Today, we're going to pull back the curtain on a really powerful tool that every top analyst and consultant has in their toolkit: linear regression. It's the engine that lets us take all that data from the past and turn it into solid predictions about the future. And that, of course, is absolutely critical for making smart business decisions. All right, so here's our game plan. First, we'll get right to the heart of what linear regression is all about. Then, we'll look under the hood to see how the model actually gets built. After that, we'll run through a real-world sales example, which is the fun part. And then, super important, we'll stress test the model to see if we can actually trust it. And finally, we'll figure out how to measure just how strong that relationship is. When you boil it down, so many challenges in business, in finance, in pretty much anything, come down to this one question. Can we look at what's already happened and use it to make a really good guess about what's going to happen next? Well, linear regression gives us a solid mathematical way to do exactly that. Okay, let's dive into section 1 and establish the core principle. At its most basic, linear regression is all about finding and measuring the relationship between two different things, or as we'll call them, variables. So what does that really mean? In simple terms, it's a way to see how a change in one thing seems to affect another. If we notice that every time variable X goes up, variable Y seems to go up too, regression is the tool that lets us put a precise number on that relationship. Now, getting these two variables straight is absolutely critical. The independent variable, which we call X, is the thing we think is causing the change. It's our predictor. The dependent variable, Y, is the outcome we're trying to predict. You can think of it as the effect. So in our little example here, the amount of rainfall predicts the crop yield. Simple, right? So how do we actually build one of these models? How do we go from just a big, messy pile of data points to a clean, single line that can give us a forecast? Let's get into the mechanics. First things first, before you do any math, you have to just look at your data. You plot it out on a simple chart, a scatter plot. Put your independent variable on the bottom axis and your dependent on the side axis. And you can see right away, do the dots kind of look like they're forming a line? Or do they just look like a random cloud? If it's a cloud, well, linear regression isn't the right tool for the job. But if you do see a pattern, if it looks like a line, then the entire goal of this whole process is to draw one single straight line that cuts through that data in the best way possible. We call this the best fit line. It's like the perfect summary of the relationship between your two variables. And that line, like any line, has a mathematical equation that defines it. Now, this might give you flashbacks to high school math, but trust me, each little piece here plays a really important part in building our model. Let's just break this down real quick. Y is the thing we're trying to predict. A is the starting point, the baseline value if X was 0. Now B, the slope, this is the real star of the show. It tells us exactly how much Y changes for every single unit that X changes. And X is just our predictor variable. Finally, that little epsilon symbol. That's just a way of saying, hey, no model is perfect. There's always going to be a little bit of random error. So, you're probably wondering, how does a computer actually find that perfect line? Well, it uses a really clever technique called the method of least squares. Basically, it calculates the distance from every single data point to a potential line, and it keeps trying different lines until it finds the one single line that has the smallest total error. It's mathematically guaranteed to give us the true best fit. Okay, that is enough theory. Let's make this real. It's time to put this tool to work on a practical business problem to see how it actually helps us make decisions. So here's our scenario. Imagine a company that keeps track of two things: how many training courses their salespeople take and what percentage of their sales quota they hit. The big question is, does more training actually lead to better sales? And even better, can we predict someone's sales performance just by knowing how much training they've done? And here we go. This is the payoff. After we run the numbers through our model, we get our very own prediction machine. We can now plug in a number for our independent variable, say 15 training modules, and the model spits out a specific, actionable prediction. We'd expect that salesperson to hit about 84.7% of their sales target. How cool is that? Okay, getting a prediction is great, but we have to ask the tough questions. Can we actually trust this number? How do we know that this relationship we found isn't just a total coincidence? This brings us to a super important step: validating the model. This is how we prove statistically that our finding is real. It's called hypothesis testing. First, we start with what's called the null hypothesis, which is basically a fancy way of saying we assume there's no relationship at all, that the slope B is 0. Our job is to prove that assumption wrong. So we calculate a score from our data, called a t-value. Here it's 5.481. Then we compare that score to a critical value. Think of the critical values, plus or minus 2.306 in this case, as the goalposts for random chance. Because our score of 5.481 is way outside those goalposts, we can confidently say, nope, this is not random. We reject the null hypothesis. The relationship is real and statistically significant. Now, what about that random error we talked about? We can actually use it to build a confidence interval around our prediction. For our model, it comes out to plus or minus about 10.5 percentage points. This gives us a practical margin of error. It means we can go to our boss and say, we predict 84.7%, and we're 95% sure the actual result will be within about 10 points of that. That quantifies our uncertainty, which is incredibly valuable. So, we've proven a relationship exists, and it's not just a fluke. But the next big question is, how strong is it? I mean, is training a huge driver of sales, or is it just a minor factor? Our last section is all about answering that. The first number we look at is the correlation coefficient, just called R. It's a really simple score that runs from -1 to +1. The closer it is to +1, the stronger the positive relationship. The closer to -1, the stronger the negative relationship. And if it's near 0, well, there's not much of a linear connection there at all. And here it is, the single most important warning in all of statistics. You have to remember this. Just because two things move together, it does not automatically mean one is causing the other. There could always be some other hidden factor that's driving both, so be careful with your conclusions. Okay, now for the big reveal. If we take that correlation number R and we square it, we get what's called the coefficient of determination, or more commonly, R squared. And for our sales example, the R squared is 79%. And this number is just beautiful, because it has such a clear and powerful meaning. It tells us that 79% of all the differences we see in sales performance, why one person hits 90% of their target and another hits 70%, can be explained by one single factor: the number of training modules they've completed. That is an incredibly powerful insight to bring into any meeting. So there you have it. We've used linear regression to find a clear, predictable, and really strong link between training and sales. And so the final question is really for you. What are the key relationships in your world? What are the hidden drivers of success that are just waiting to be discovered? The data is probably already there. You just need to apply a framework like this to find it.